Hello everyone. I'll try to make videos for all the topics which are there in GATE. And so first let us begin with open channel flow. So open channel flow is, by the name itself we can see that which occurs in an open channel, but this is not the proper definition of the open channel flow. The the basic requirement in open channel flow is the top surface of the fluid, which is water normally, it should be at atmospheric pressure. The channel can be of any shape, it can be trapezoidal, it can be a rectangular channel, triangular channel, or maybe a circular channel also. But the top surface will still be at atmospheric pressure. Whereas in the pipe flow, the complete circular pipe will be under pressure, and so the driving force in pipe flow will be pressure, whereas in open channel flow it will be gravity. And so basically it is driven by gravity, so we consider the Froude number in this case, and in pipe flow we see the Reynolds number. So this is the basic difference between the two. And one more thing we can see is, if it is an open channel flow, then hydraulic gradient line, which is the sum of, let's say this is the datum, so this height will be something z1 and this is something y1. So the hydraulic gradient line will meet the top surface of the fluid, like the hydraulic gradient line and the top surface of the fluid will be the same. Whereas if it is a pipe flow, it will be always above the pipe surface. If this is the pipe from datum, and so hydraulic gradient line will be somewhere above the surface. So let's move on to the types of channels. So first of all, there are some classifications of channels. First is prismatic channel. So if in a certain length of the channel, if its cross-sectional properties such as its shape, length, width and depth, and slope of the channel bed, if these are not changing, then we call it as a prismatic channel. Normally man-made channels like canals, these are the prismatic channels. And in non-prismatic channels, we can take example of river. The cross-sectional properties such as depth, width and the slope of the channel, so these may change in a certain length of the channel. It won't remain, it may remain same or it may not remain same, we cannot say that. So it is called as a non-prismatic channel. Another classification is rigid boundary and mobile boundary channel. This classification depends mostly on the boundary characteristics. So if the boundary is such that with time and with space, its roughness is not changing and the shape is also not changing, which means if it is having a certain roughness at time t1, so we say for some years or some months this roughness won't change, and same holds with the shape also. So if it is not changing, then it is called as a rigid boundary channel. And in rigid boundary channel, only one thing is there which can vary, that is the depth of flow. depth of flow may change. So it has a 1 degree of freedom. Now if the channel is such that, like, with time the velocity and shear stress is such that it erodes the boundary particles and there may be deposition also. So if that is happening with space and time, if we are traveling for the river is traveling for going for some distance and these characteristics are changing, the shape it is not holding and the roughness is also not the same throughout the length, then it is called as a mobile boundary channel. So how many things are there which can change? It is the shape of channel, and then width, depth, and slope. So there are four things. So it has a 4 degree of freedom. So in our case we will only consider the rigid boundary channel and we'll work upon that. Now there are flow classifications in open channel. So let us go through them one by one. First is steady and unsteady flow. Steady flow means the flow characteristics such as discharge, velocity, and flow depth. These are not changing with time. So if I take the partial derivative of discharge with time, it is going to be 0. Same is for velocity and depth also. So we are only considering a section in this case. So if I'm seeing this section, these properties are not changing with time, but it is not like the discharge is, maybe it is something q1 here or q2 here, so these are different, but at this section also it is again not changing with time. So this is called as a steady flow. And again, if these parameters are changing with time, then the derivative will not be equal to 0, and in that case it is known as unsteady. Next classification is uniform and non-uniform flow. Uniform flow refers to the space dimension. Let's say this is some distance s, and again the same flow parameters discharge, velocity, depth. If in this channel length these parameters are not changing, which means their partial derivative with respect to space is 0 because it is not changing. So it is termed as a uniform flow. Whereas if these parameters are changing in this length, then these derivatives won't be equal to 0, will have a certain value. So it is known as non-uniform flow. This is possible in a prismatic channel where all the parameters are remaining same, and this non-uniform flow is possible in a natural channel. Here is one thing is to notice is only steady uniform flow is possible in nature. Unsteady uniform flow is practically not possible. So what we are saying is, if at a certain time instant t1 the flow is q1 and here also it is q1 at t1. If the time is changing to t2, next instance is t2, and the flow is changing to q2, so this is not possible in nature. Next classification is gradually and rapidly varied flow. So these are the classifications in non-uniform flow, because mostly the depth will change. The width may also change, but what we will study will be mostly about the depth. So if there is a obstruction in the flow due to some dam, so the water was going at some level like this, and it will rise due to the obstruction. So there is a change in depth, and which is happening in a long distance. This will be in kilometers, and it is not visible by the naked eye. There will be a change, but it will be so gradual that we cannot see it. So it is called as gradually varied flow. And if the change is occurring in a very small length, like in case of a hydraulic jump, it it will be something like this, and depth will change in a very small length. This length will be very small, so it is called as rapidly varied. Now there are they it they have their own classifications in steady and unsteady. So steady and unsteady means if it has attained a particular condition which is not changing with time. Like we can see in this case, if it is a dam, so there will be a certain discharge coming, and it won't change with time unless there is a flood or something. So we can generalize that it won't change with time, so it will be a steady condition. And if we see if there is a some flood in the river, so there will be a sudden increase in the discharge, and then that discharge will go. So the with time the discharge is changing, so the depth will increase gradually, but the discharge is changing at different times, so it is a unsteady flow condition. And in rapidly varied flow, if it is a hydraulic jump with a particular velocity and depth, so these parameters are not changing with time, so this we can consider as a steady condition. On the other hand, if there is a surge in the channel, if there is a gate and the water is going like this, and this surge will move with time in this direction, so the depth will change rapidly, and so the condition won't remain as steady, so it will be rapidly varied but unsteady flow. So the next classification is spatially varied flow. Spatially, so if there is an it normally occurs if there is an addition of water in the channel or there is some withdrawal. So if there is some discharge q, delta q is adding from here, so it will be q plus delta q. So in this length the discharge is increasing because of some spatial addition. So it is a case of spatially varied flow, and it may happen also that discharge is going out, then also it is safe. Next classification is laminar and turbulent flow. It is classified based on the Reynolds number, which is in this case which is given as Vd upon nu. Here d is taken as either the hydraulic radius or hydraulic depth. So the governing numbers are if Reynolds number is less than 500, it is a case of laminar flow. And if it is greater than 2000, it is a case of turbulent flow. In between these two, it will be transient flow condition. Next is critical, subcritical, and supercritical flow. It is defined basically on the base of Froude number, which is given as V upon under root GD. Here D is the hydraulic depth, or we call it the characteristic length, which is given as area of cross section divided by top width. In case of a rectangular channel, the top width will be equal to the bed width, so it will be equal to the depth of flow. But in case of trapezoidal channel, it will be different. So based on this, if the Froude number is equal to 1, it is the case of critical flow, and if it is less than 1, it is subcritical, and for greater than 1, it is supercritical. We will be looking at these terms in detail when we study specific energy and all. For now, this is okay. Next is the velocity distribution. So velocity distribution is considered as a logarithmic or power law profile, which goes something like this. It should be like this, but the maximum velocity is not attained at the top, it is somewhere below the top. So it is basically due to the secondary currents in the section. So in a section, because of the boundary, there will be zero velocity everywhere on the boundary, and it will increase as we move inside the channel. And so it will have a certain maximum at some depth below the surface. And to find out the average velocity, we take either v at 0.2 plus 0.8 upon 2. We take these two measurements at 0.2 meter and 0.8 meter, and we take the average of these two, or we take as v at 0.6 meter. So basically, if we are taking two observations, so this is more reliable. And another formula is, this is k times of velocity at surface. So depending upon the condition, this k varies from 0.8 to 0.95. Next is the pressure distribution. So pressure is assumed hydrostatic in this case, which means that at any point pressure will be equal to the weight of the fluid which is there on the top of it, like this. So as we have seen this formula, P equal to gamma h, this is h. So at this point pressure will be equal to P equal to gamma h, and if this channel is having a very large slope, and this will be like this, and this is equal to gamma if this angle is theta. This is gamma h cos theta. We can see it from if at any point in this section, like here, there will be a pressure acting in this direction, and weight of the fluid will be something vertical from here. This is the weight, and this angle is theta, so this will be W cos theta. This is W, and this will be balanced by P force. So if we say sigma f y equal to 0, then, and if this length is delta L, so P into delta L, and if we consider a unit weight, will be equal to weight of the fluid, and weight of the fluid we can write as delta L into gamma into 1 cos theta. From here P is equal to, this will be cancelled, into Y also, so gamma Y cos theta. So basically we assume the hydrostatic distribution in this case. Next is the momentum equation. This is used to derive various things. Basically mostly we use it for hydraulic jump, because we'll see that in later, like, because energy, there is an energy loss in hydraulic jump, so we cannot find out the loss directly, but in momentum equation only the external forces are there, so we use the momentum equation to find out the hydraulic jump depth. If these are two sections, and there is some pressure from here, P1, P2, V1, V2, and the depth is Y1 here, Y2 here. So momentum equation, it states that from the Newton's second law of motion, rate of change of momentum is equal to the resultant of all the external forces acting on the body. So if the rate of change of momentum, as in momentum out minus momentum in, you can say the from here momentum out is m2 minus momentum in is m1, is equal to the sum of all the external forces. So if we consider this side as positive, it is equal to P1, which is a pressure force, minus P2 plus, if the weight of the fluid in this is W, and this angle is theta, so this will be W cos theta. And and here because of this boundary there will be some friction. Let's say that is F. So it is equal to P1 pressure force at section 1, P2 pressure force at section 2, and one more component in the direction of flow will be W sine theta. So it will add to the force here plus W sine theta minus this friction will be opposing the flow, which is minus F. We can expand these expression. For momentum we can write rho q v2, this is mass per second into velocity, minus rho q v1 is equal to gamma a1 y1 minus gamma a2 y2 w sine theta minus f, and we can solve this if it is required. Now the special case of this condition is if the channel is frictionless and horizontal. So we can derive the specific force from there. If it is section 1 1 2, 2, we are making two assumptions here. Channel is horizontal and frictionless. So there will not be any component due to the weight of the fluid in this direction, and there won't be any frictional force. So only two force will remain, that is the momentum at this section and the pressure at this section, and the pressure at this section and momentum at this section. So we can write as momentum out minus momentum in is equal to the sum of external forces, which is in this case P1 minus P2. So if we rearrange it, it is P1 plus M1 equal to P2 plus M2, and if we divide it by the unit weight of the fluid, so this quantity P plus M by gamma, it is known as the specific force. We'll look into it when we are doing the specific energy in the channel, and there will we see about it more. So it is the sum of the pressure force plus momentum flux. Pressure force plus momentum flux in the unit weight. Pressure force plus momentum flux per unit weight of the fluid. Next is the energy equation. So if it is having some slope, energy equation is basically just the Bernoulli's equation which we apply here, and if it is having a datum here, this is section 1, this is 2, so there will be some velocity v1 v2, this is z1 z2, this height is y1 and this is y2, and due to this velocity here it will be some energy v1 square upon 2g is the kinetic energy, and here it will be V2 square upon 2g. So and there will be some head loss also if we are not assuming the ideal condition. So by the Bernoullis we can write it as Z1 plus V1 by gamma plus V1 square upon 2g is equal to Z2 plus V2 by gamma plus V2 square upon 2g plus head loss. And now there is a special case in this. If we take a horizontal channel and assume no friction, and so there will not be any head loss. And so if this is horizontal and we are assuming the channel bottom as our datum, so let's say z is equal to 0, and this is y, here y1 and y2, and above it, because of the velocity, there will be some velocity height v1 square upon 2g and v2 square upon 2g. So if we write the energy equation again, it is z is equal to 0, so only p1 by gamma plus v1 square upon 2g, v2 by gamma plus v2 square upon 2g. Here if we consider these the bottommost point of the channel, so p will be gamma into y1, because the distribution we are assuming is hydrostatic, so p is equal to gamma h gamma y1. So gamma y1 upon gamma plus v1 square upon 2g is equal to gamma y2 upon gamma plus v2 square upon 2g. So from here we find this y1 plus v1 square upon 2g, y2 plus v2 square upon 2g. Here the term y plus v square upon 2g, this is known as the specific energy, which is the total energy above the datum. So we are removing the datum head from here, and whatever is remaining is our called as specific energy. In the next video we will do the uniform flow.